So, this brings us to the concept of a Wigner distribution. We have time and frequency. Okay. So, what is a Wigner distribution? In a Wigner distribution, it is a distribution, there are other such strategies too, which captures essentially both the temporal and frequency information of a pulse in one map, in one portrait if you wish. Okay. So, this is like my passport photo, it is a two-dimensional ID of me. An Aadhaar number, a social security number is a sort of fairly 1D identity of a person. Of course, a retina scan is 2D identity, a fingerprint is a 2D identification of a person, right. While there can be a lot more of ambiguities with the 1D identification leading to impersonation and whatever not, some of these 2D identifications simply work in disambiguating or establishing identities better, right. So, therefore, of course, their dimensionality has increased. Here we are compelled to go for a higher dimensional identification for the pulse, simply owing to the way in which we represented the pulse itself. We essentially had I of t and we had phi of t as well, or s of omega and phi of omega. So, accompanying this we have the notion of the instantaneous frequency nu of t. We may have written this earlier as nu naught minus d phi by dt and so on, but that is just a convenient way of representing this whole thing, right. What this essentially means is that the a unique identification, unique mapping of various different pulses needs to be done on a 2D distribution or 2D whatever interferogram. This is not an interferogram, a 2D map, where on one axis we capture time, on the other axis we capture the instantaneous frequency for the pulse. Okay. So, such a map is a Wigner distribution. For an unchirped pulse, the Wigner distribution looks like this. How we arrive at it, we will see. It is an ellipse. Okay. Now, if we plot the amplitude of the pulse alongside on the same temporal scale, the amplitude would have looked like this, right. So, let us say this is the square root of I of t. Now, what we measure on a spectrometer is dominated by the spectrum coming from this central region of the pulse, is not it? A spectrum could have been derived from any temporal slice within this pulse. Any of these temporal slices could have resulted in producing the S of omega which we are sort of seeking for one part at least. Whereas, because this is a detector is going to pick up the weighted sum of all these spectra, the most intense regions of the pulse will make dominant contributions to the spectrum. So, therefore, if I measured only the spectrum, right, it is no surprise that if we measured only the spectrum of the pulse, we would not be able to really calibrate the pulse very well, because the central region alone does not look very different even on a Wigner distribution. It is just a elliptical patch. Whereas, if we can do something to produce the entire Wigner distribution, if for an unchirped pulse, this is a set of horizontally aligned contours and this is a set of tilted contours, elliptical contours on this 2D map, this can give us hope for uniquely identifying a pulse. Now, why are we bringing this up? First of all, we need to have some feel for what could be the unique ID of the pulse, isn't it? Whether it's the retina scan or the finger scan. So, we have established what type of scan we would like to do, at least one of those types, which is a Wigner distribution, which is a time frequency map of the pulse. Okay. So, a mathematically rigorous form of a musical score in some sense is a spectrogram. Okay. What do we mean by a spectrogram? Okay. So, if E of t is the waveform of interest about which we are concerning ourselves in this process, then its spectrogram per definition, it is a new term. Its spectrogram per definition is the waveform itself, and the spectrogram depends upon the gating function that we use, multiplied by a gate. You take the Fourier transform of the product of this function. Finally, we are going to only be able to measure intensities, irradiances, whatever we measure. What do we measure in a detector? The absolute value square of something for infinite time. That is what any detector is going to measure, whether it is a spectral detector, a spectrometer or whatever not. This is mandatory, it is imposed on us, right. So, this quantity is called the spectrogram of the pulse. So, this kernel, of course, this part of the kernel is of course owing to the Fourier transform, right. So, this is a variable delay function. So, produce the spectrogram, produce this Fourier transform of the waveform and the gating function and absolute value square it for every value of delay. That is what we call the spectrogram. Okay. It is a function of omega and it is a function of tau, the delay. Okay. It is a set of all the spectra of temporal slices of E of t. That is what it is, right. Now, we come back to where we were. Oh, okay, that color has changed to yellow, but I think you can still read the heading, right. So, that is okay. Now we come back to our earlier notion of looking at the waveform as a spectral signal E of t with a time varying instantaneous frequency nu of t, and the gating function here is g of t. So, you gate this out using the gating function and measure the spectrum. Do this for various delays of tau. Understand that you need to scan the gating function over the waveform only in the region where the waveform itself has appreciable amplitude. If E of t goes to 0, like if E of t goes to 0 or very close to 0, I mean if it is Gaussian or it goes to the noise level in a practical measurement, then you are not going to get any appreciable signal from there. All you need is to scan this region with your gate function. And record the signal for each position of the gate function relative to some reference. Again, what do we take as the reference? We take the maximum amplitude point as the reference for 0 delay, but it is just a reference. You in fact have to fix it post facto, the reference point, when you do these delay scans, as I told you earlier, right. So, that this helps us generate the spectrogram of the waveform of interest. Okay. So, essentially this is what we have been plotting all through. The instantaneous frequency changes as a function of time as we go through, right, and using the gating process, we can measure the spectrogram of the waveform of interest. If we do this, we could get something like the Wigner distribution, which becomes a unique ID at least for the pulse, but to match the ID and the person is another matter. Figure out uniquely what the pulse is, that is part 2 of the story, which I have not sold you yet. I am just trying to convince you that getting the Wigner distribution is a sort of way forward. At least let us get there and land ourselves, hopefully not land ourselves in too much trouble, right. Okay, this animation for what it's worth, let me try and redo it later. There's some. Now, for linearly chirp pulses, positive or negative, right, with the time frequency axis being what it is, the spectrograms which we measure essentially have different tilts, as has been shown in these distributions. Just like a musical score, the spectrogram also visually is different for different kinds of pulses, right. So, let us examine some of the properties of a spectrogram. Okay. Why are we chasing this strange integral where I take a function multiplied with a gating function, do its Fourier transform and take the absolute value square of that, right. And finally, I am again measuring only intensities. Why are we obsessed with it? I state this without proof. Algorithms exist where we can retrieve the waveform E of t from the spectrogram. Now, I was just telling you that in the 1D world, in 1D this retrieval problem does not work, this phase space is too limited. But in the 2D world, okay, you are going from flat line to 3D in some sense. In the 2D world, there is, it is rich enough that we can invert the spectrogram to retrieve E of t uniquely. This is a statement of mathematical nature. So, it is true. For us, the problem is going to be how do we get the gate and do this. We have just the pulse itself. Where is the shorter gate? I have oversold the idea of the spectrogram to you, or I am overselling it maybe, but unless we find the gate, it is just a very nice mathematical theorem to prove and maybe publish at some point. There is no further applicability in real life. A unique two-dimensional identification is a great idea, but unless you have the fingerprint or the retina scan or whatever and that available and accessible, there is no point in establishing a standard. That is exactly the case where we are now. So, the spectrogram essentially can uniquely determine the waveform's intensity and spectral phase both in the time domain. Okay. Ambiguities could still exist, but we need to make a benchmark, a catalog and be able to identify cases where there could be ambiguities. Okay. So, the other thing is that the gate function, we are coming to the crux of the problem. Ideally, it seems the best gate function is going to be a delta function. That is the best gate. If I take the delta function as the gate function, do this, right, then we have the narrowest gate. It gives you the finest, gate or window to look through and scan the finest resolving window function to scan the waveform and get information about it, right. That it seems is the best gate, but if we idealize it and use a delta function for the gate, look at what is going to happen. Use the delta function over here. This essentially does the following, that it forces these two t's to become just tau, that is all the delta function does, and what we get here in the end is just the intensity profile of your waveform. But this you already did in interferometry. In linear interferometry, you got intensity information about the waveform. So, this trivializes the process of approaching this problem and resolving it through the use of a spectrogram. Okay. So, therefore, the gate function should not be much shorter than the pulse. This is not obvious, this is not intuitively obvious or obvious that we need a gate with substantial temporal width. Okay. So, now here comes the technique of interest, okay, where somebody, the group of Rick Trebino and other co-workers developed a technique where we can do optical gating. Right? We have this technique called frequency resolved optical gating, which acronymizes nicely to the word frog. Okay, so therefore, the inventors of this technique in good humor named all the variants and other techniques either after amphibious creatures of various kinds such as frog in English, or variants of it called grenouille, which is the French word for a frog, or other amphibious or creatures from the animal world, another technique called spider, which is also related, right. So, this is what, so these techniques are ways of implementing the spectrogram that we were seeking. First, let us see how to get to the spectrogram, because someone told us that the spectrogram can be inverted to retrieve the waveform E of t, if we take that statement seriously. So, we need this signal, take its Fourier transform, the signal contains the waveform, a product of the waveform and the gate, take its Fourier transform and build up the intensity signal. We call this intensity because we are essentially absolute value squaring this field quantity, right. So, how is frog even implemented, right. So, take this, the initial part of any of these implementations is just the same. Up to this point in the setup, all we have done is taken a pulse, taken the waveform, the pulse E of t, generated a faithful replica of it, E of t minus tau, okay, these two, and we can take any of the earlier interferometric techniques other than the lowest order or first order. Take the second harmonic, second order interferometry, or here we have the third order interferometry, right. Take the same third order interferometry, and here instead of the detector or camera or photodiode which you used earlier, introduce a spectrometer and measure the spectrum instead as a function of delay. Measure the spectrum as a function of delay tau. If we do that, unlike earlier where we did not have this Fourier transforming step and getting the spectrum out, now we have the Fourier transformer, which is the spectrometer, that gives us the realization of the spectrogram, which is the frog intensity, which is a function of two variables, omega, the frequency contained within the pulse, frequency is contained within the pulse, and tau, the delay that is introduced in this process. Where is the gate? Where is the gate? The gate is a copy of the pulse itself, is the gate. We did not want too short a gate, we have the copy of the pulse itself, right. But then it is interacting in a nonlinear medium, so there is, it is not just as long as the pulse itself, the gate shrinks in its time width owing to the fact that there is nonlinear interaction. Okay, the nonlinearity shrinks the gate to something which is smaller than the in width than the pulse itself, but not all too small. So, the frog technique, okay, is one in which this quantity E of t minus tau, the absolute value square, in the case of the third order realization, gates out a piece of E of t, the waveform in itself. How is that? So, have a look at it. This is the waveform of interest. I have made a copy of it and delayed it with respect to this waveform of interest. There is some temporal overlap between the falling tail of the signal and the rising edge of the gating pulse. Okay. Now, you could argue that this white thing here is the waveform and the thing on the left is the gate. It does not matter which you call the gate, which you call the pulse. They are identical copies of each other except being time delayed insofar. So, what you call is matter of choice, it is just that we have sketched it like this. But the key point is the signal that we are measuring arises from this overlap region where both of them have appreciable non-zero overlap, that is this window in time. It is a product of these two functions, right. It is a product, the signal here for the third order autocorrelation is a product of the absolute value square of this times the electric field. That is Kerr nonlinearity at work basically. Had it been second harmonic, this would have not been absolute value square of E of t minus tau. E of t minus tau would have been the gate. Okay. So, that is, but then you need to measure the spectrum in this case. Okay. You need to measure the spectrum of the pulse, and when we do this thing very nicely, we would be able to generate the spectrogram of the pulse, which is for every delay value, every slice for every delay is a spectrum. For example, if I take a delay cut like this, the spectrum would have been something like this is the omega axis, this is the S of omega axis. So, I have just taken a line cut over here. If I took another line cut over here, the spectrum could have been like say something like that. So, it is a 2D carpet of spectra measured as a function of delay. The horizontal axis is time, but it is delay. Okay. So, much like the musical score, frog trace also is a plot of the time versus frequency. We have just realized that the spectrogram in real life, that is what it is, right. So, now the frog trace for more complex pulses. Now, look at what we were seeing earlier, right. We had various kinds of scenarios where we could have self phase modulation occurring in a pulse, we could have some cubic spectral phase happening in a pulse, we could have had double pulses. The nice thing about it, okay, nice thing about it is the frog trace reflects each of these. Okay. Here we have a quadratic sort of phase dependence, instantaneous frequency could vary quadratically with respect to frequencies, here it could be something else, here it is even something else. The frog trace, as it should be for each of these scenarios, should produce a unique two-dimensional stamp for the pulse, right. So, frog trace is indeed the spectrogram of the pulse, right, where we have substituted E signal in the expression for the frog trace. Here we simply have used E of t minus tau the whole square for the third order nonlinearity being used in frog. We have used this to be the gating function, right. Now, because we know the order of the nonlinearity, we can essentially figure out we can address the inverse problem where we retrieve the waveform E of t from the spectrogram I frog of omega tau. So, that is the retrieval part of it. So, we need to know the gate variable. I am sorry, I will correct the fact that these headings have changed color for whatever reason. Now, okay, we just have a few minutes. I will set this up and come back to the retrieval part in the next lecture. So, what we have done so far is we have essentially done a 1D Fourier transform of this two-dimensional function E signal t of tau in the process of making this interferogram. Okay. This is a 1D Fourier transform with respect to a particular a corresponding frequency variable which is gamma, and we will need to somehow pull out the input pulse, the unknown waveform from this 2D information which we have in some form, which is essentially the frog spectrogram I frog of omega t. Okay. So, what we need is to get from this, we need to get this, and from this we need to get this. So, that is the retrieval or inversion problem that we are going to address. Okay, in this course we are not going to rigorously like sort of develop the algorithm. I will point you to some literature. We are going to understand the spirit in which this is done, and then one can write iterative programs which iterate through this process and lead us to the goal of measuring I frog and retrieving E of t, the unknown waveform. So, we are getting close to that. Okay. With that, we will stop for today and meet next week. Meanwhile, if you have any questions, I am happy to take them.
How loss sensitive is this?
Pardon?
How loss sensitive is probably?
How?
Loss sensitive, like how much does loss affect the
What loss?
like fiber loss sensitive? The delay that
There is no fiber here.
the delays that you create,
Mhm.
always be some loss.
Yeah, there can be losses.
So does it affect it or not? It's like
As long as the spectrometer can record a spectrum, you don't care, right? That's as much as loss would affect it. If the instrument of also usually instruments can introduce their own distortions. So, we need to get a measure of that. But remember that this is an interferometer. You can always use a white light source to characterize the interferometer / the spectrometer at any point of time. So, one needs to of course calibrate the setup in the delay domain as well as the frequency domain. That one needs to do as one would for any this thing. Then loss or otherwise does not substantially matter. Of course, one needs to ensure that the bandwidth of the pulse is that the optics that you use in this system handles the entire bandwidth of the pulse. So, we need to know something about the pulse. I cannot use an optical spectrometer and do a measurement of a pulse in the mid infrared. The spectrometer operates in the range 0.3 to 1 micrometers, but my pulse is in the 2 to 3 micrometer range, my pulse spectrometer. That is a sort of no brainer, right. So, all these things of course we need to set right, but after those basic sanity checks, there is very little that one needs to do in these contexts. That is the important part.